In mid-2018, deep inside Nintendo's corporate headquarters in Kyoto, senior executives and hardware engineers believed they had secured their platform. Months earlier, their flagship console, the Nintendo Switch, had been compromised by a flaw so surprisingly simple it caught the company's security architects off guard. The entire multi-billion-dollar security ecosystem of the console had been bypassed, not with a high-tech software exploit, but with a bent paperclip bridging two microscopic gold pins on a Joy-Con rail. That single physical vector exposed millions of devices worldwide to custom firmware, unauthorized operating systems, and game piracy. But Nintendo did not merely issue a software patch to hide the damage. They knew that a software patch on a compromised hardware foundation was nothing more than a temporary bandage. Instead, they went back to the silicon drawing board. Working alongside NVIDIA's chip design team, Nintendo re-engineered the console's main processor. They rolled out a revised system-on-chip, codenamed Mariko. Inside this revised silicon, they updated internal cryptographic paths, hardened the boot sequence, sealed memory buffers, and patched known hardware and software entry points. The revised processors were sent straight to manufacturing assembly lines, sealed inside newly packaged retail boxes, and shipped to store shelves across the globe. On paper, the revised Nintendo Switch appeared virtually impregnable. Known software attack vectors had been closed, unencrypted memory buffers were sealed, and no paperclip trick could short a data line again. They appeared to have constructed a digital vault wrapped in hardened silicon. Yet, less than 18 months later, that security architecture fell apart. It did not fall to a supercomputer, an army of state-sponsored hackers, or a leaked master key. It was brought down by a fingernail-sized circuit board, soldered directly to the motherboard, executing a physical attack that lasted less than 1/millionth of a second. A sub-microsecond voltage drop, a deliberate surgical power starvation, forced the console's processor to misread its own security commands. This is the story of how hardware modders stopped attacking Nintendo's software, turned the fundamental laws of semiconductor physics against the company, and broke the updated Switch. To understand why Nintendo was confident that their updated console was protected, you have to understand how modern computing hardware boots up from a cold start. When you press the power button on a gaming console, the machine does not simply start loading a game or opening its user interface. It wakes up in a state of absolute paranoia. Before it trusts the operating system, before it initializes graphics drivers, and before it reads a single byte of code from internal storage, the console must verify its own hardware identity. Engineers refer to this foundation as the hardware root of trust. Deep inside the silicon wafer of a modern microprocessor sits an immutable, read-only block of memory known as the boot ROM. The boot ROM is created at the semiconductor fabrication plant when the silicon wafer is forged. Once it is physically etched into the silicon, its code can never be modified, rewritten, or erased by any software update. It serves as the absolute foundation of the entire console's security model. When electricity hits the processor, the CPU instantly begins executing the instructions stored inside that read-only boot ROM. The boot ROM acts as a zero-trust security guard standing at the front entrance of the system. Its job is to look at the next stage of software, the boot router, and verify its digital signature. The boot ROM verifies the next boot stage against public key material anchored in the processor's eFuses, while Nintendo retains the corresponding private signing keys. If the cryptographic signature matches, the boot ROM guard opens the gate and allows execution to proceed to the next phase. If verification fails, the boot process enters a failure path and refuses to execute the untrusted stage. When the original Nintendo Switch launched in March 2017, it was powered by NVIDIA's standard Tegra X1 processor, known internally as the T210. That chip contained a fatal flaw buried deep inside its boot ROM code, a vulnerability dubbed fusée-gelée, discovered independently by hardware security researchers including Kate Temkin. By holding down the volume up button, sliding a tiny plastic jig with a bent piece of wire into the right Joy-Con rail to ground pin 10, and plugging in a USB cable connected to a computer or smartphone, users could force the Tegra chip into USB recovery mode, or RCM. Once inside RCM mode, a basic software payload could cause a direct memory buffer overflow inside the boot ROM itself. Because the boot ROM code failed to validate the length parameter of incoming USB control transfers, an overly long data packet could overflow the stack buffer. This overflow allowed code to overwrite execution memory and bypass the boot ROM guard entirely before it ever verified the bootloader's cryptographic signature. Millions of original Nintendo Switch consoles were exposed to this vulnerability. Because the flaw was buried directly inside the unwritable boot ROM silicon, no over-the-air firmware update could permanently fix it. If Nintendo pushed a system update to block custom code, modified consoles could simply use their hardware-level access to block the update or downgrade their operating system back to an earlier version. Nintendo realized their software security on early units was unfixable over the air. Their only path forward was to revise the chip design and forge a new processor. In late 2019, Nintendo officially introduced the Switch Lite alongside a revision of the original flagship console. On store shelves, these updated units were virtually indistinguishable from the originals, save for a red-themed retail box and significantly improved battery life. But beneath the plastic casing, Nintendo had replaced the original 20nm Tegra T210 processor with a new 16nm silicon shrink codenamed the Tegra T210B01, colloquially known in developer circles as Mariko. NVIDIA's silicon engineers systematically addressed the entry points hardware hackers had exploited over the preceding 2 years. First, they revised the boot ROM code embedded in the silicon, fixing the USB control transfer buffer overflow. Plugging in a paperclip jig, grounding pin 10, and sending a payload over USB now did absolutely nothing. The memory buffer was sealed against software overflows. Second, the revised platform retained hardware anti-downgrade controls. During selected system updates, authorized boot software could burn additional version fuses inside the chip. Early boot code compared the fuse state with the firmware generation and rejected incompatible older boot stages, blocking software downgrades. Third, Mariko introduced a revised boot security design, including encrypted BCT data and tighter security engine key slot handling, reducing opportunities for software to observe sensitive key material. From a pure software security perspective, known attack paths appeared closed. You could not run custom software without a bootloader digitally signed by Nintendo. You could not obtain a signed bootloader without Nintendo's private master keys. You could not extract keys without executing custom code at the kernel level. And you could not inject custom code because the USB boot ROM buffer overflow was dead. The software security loop seemed sealed. But software is an abstract mathematical concept, while the physical chip executing that software is bound by the chaotic, volatile laws of physics. To understand how independent hardware researchers bypassed this revised chip, you have to look beyond binary code, programming languages, and cryptographic algorithms, and look at what a microchip actually is at an atomic level. Inside the NVIDIA Tegra Mariko processor, over 2 billion microscopic transistors are packed onto a piece of silicon no larger than a fingernail. These transistors function as ultra-fast electronic switches. When a high voltage level, roughly 1.1 volts, passes through a conduction path, the processor interprets that electrical state as a binary 1. When the voltage plummets to 0 volts, the processor reads it as a binary 0. Every operation the CPU performs, every arithmetic equation, every signature verification, and every memory fetch occurs in synchronization with a master clock signal. This clock acts as a conductor, beating a drum millions or billions of times every single second. On every beat of that drum, millions of transistors flip their internal states. Tiny capacitors charge and discharge, and electrical current flows across micro pathways from memory registers to execution pipelines. For a processor to calculate data accurately, the electrical voltage supplied to its core must remain extraordinarily stable. If the core voltage drops too low, transistors do not receive enough electrical energy to charge up and flip their states in time before the next clock pulse arrives. When that happens, binary ones fail to register, turning into binary zeros, and data corruption occurs. Under normal operating conditions, a sudden drop in voltage leads to an immediate system crash. Semiconductor manufacturers spend years designing complex power delivery networks packed with decoupling capacitors specifically to filter out power fluctuations and prevent voltage drops. But hardware security researchers asked a radical question. What if you do not let the voltage drop by accident? What if you deliberately starve the CPU core of electricity for a fraction of a microsecond, at the exact nanosecond the processor is evaluating its boot code? This technique is known in hardware security as voltage fault injection, or voltage glitching. The concept was not entirely unprecedented in console modding. Long before the Nintendo Switch, underground engineers had broken the Xbox 360 using a timing attack known as the Reset Glitch Hack, or RGH. By sending precise electrical reset pulses to the CPU's reset line, hackers forced the Xbox processor to skip security checks during boot-up. If you want to see how that original hardware war forced Microsoft into a multi-million-dollar silicone redesign, we broke down that entire engineering timeline in our dedicated Xbox 360 documentary, linked in the card above. In academic security laboratories, comparable laboratory fault injection research often relied on platforms such as Chip Whisperer to map out instruction vulnerabilities. But shrinking that laboratory equipment down into a consumer device would require unprecedented precision. Conceptually, a successful fault prevents an authentication failure from being handled correctly. The precise electrical fault may affect instruction execution, data evaluation, or pipeline timing. From the outside, the result is that the BCT authentication stage accepts a path it should have rejected. During that sub-microsecond window, the precise moment where the CPU is evaluating early boot code, the core voltage rail is temporarily starved of power. The core voltage rail drops from 1.1 volts down to 0 volts for just tens of nanoseconds before being restored. When the CPU is starved of voltage for that tiny split second, its internal logic gates fail to evaluate electrical states correctly, transistor propagation delays spike, and instruction or register evaluation fails. Instead of halting execution, the system slips right past the security check and continues into the next instructions in memory, treating unsigned code as if it had passed authentication. The door did not open because someone found the key. It opened because someone struck the physical lock at the exact microsecond the bolt was sliding right past the frame. If you're finding this technical breakdown insightful, make sure to hit the subscribe button below. We produce deep-dive technical documentaries on hardware security and silicone architecture every week, and your support directly helps us continue producing these exhaustive research projects. Executing voltage fault injection in a laboratory workbench with expensive signal analyzers is standard academic research, but executing that same attack inside a compact, portable consumer device powered by a battery requires solving immense engineering challenges. First, targeting and timing. You must hit the voltage drop within an ultra-precise window of just tens of nanoseconds. Second, overcoming decoupling capacitors. Motherboards are covered in tiny capacitors designed specifically to smooth out power dips. If an external circuit tries to pull the power rail down to ground, those capacitors dump their stored energy back into the trace, buffering the voltage drop. Third, miniaturization. The breakthrough arrived in the form of custom hardware mod chips, engineered by an underground development group known as Team-Xecuter, who branded their devices the SX Core and SX Lite. These tiny add-on circuit boards featured a high-speed FPGA, a dedicated microcontroller, a precision MOSFET transistor switch, and micro-soldering ribbon cables. Installing these chips moved hardware hacking out of the realm of simple software usage and into the realm of microsurgery. Micro-soldering tiny 0201 packaged surface mount components barely larger than a single grain of sand, require steady hands, specialized hot air stations, fine-tip irons, and optical magnification under stereo microscopes. To help installers diagnose hardware connections and timing states, mod chips were programmed with diagnostic LED indicators. These LED signals vary depending on mod chip firmware family. Under open-source Picofly firmware, the onboard debug LED uses standardized color sequences: blue for active glitch attempts, white for firmware flashing, and yellow to signal specific diagnostic codes through combinations of long and short pulses. For example, a pulse pattern of one long flash followed by two short flashes indicates an eMMC initialization issue, while two long flashes and one short flash indicates the CPU reached the boot stage without responding to the glitch pulse. Conversely, mod chips running firmware like Spacecraft NX or HWFly Instinct use a different visual language, pulsing a steady yellow light during their initial boot setup sweeps before glowing solid green upon a successful payload execution. Here is how that surgical strike executes inside a Mariko switch every time you press the power button. The moment power is applied, electricity flows into both the Tegra processor and the mod chip simultaneously. The mod chip connects to the console via micro-soldered flex cables, listening directly to eMMC command and data activity on the bus lines. The mod chip's logic monitors bus states, watching for specific activity that signals the microsecond the boot ROM begins its BCT verification sequence. The instant that activity is recognized, the mod chip starts an internal hardware-timed countdown. When that timer hits 0, aligning with the processor evaluating the security check, the mod chip fires its onboard MOSFET switch. The MOSFET creates a brief short circuit, pulling the CPU's main power rail straight to ground for a window of tens of nanoseconds. The CPU voltage plummets. Inside the silicon, instruction evaluation corrupts, and the CPU skips the error path. The MOSFET opens, power stabilizes back to 1.1 volts, and the CPU resumes executing code, now running custom bootloader payloads loaded straight off the microSD card. The entire glitch execution takes place in a fraction of an eye blink. If the glitch fails, the chip resets the CPU and tries again. Within seconds, the chip reports success according to its firmware-specific indicator pattern, the display illuminates, and the custom payload begins loading. Except, when a newly modded console is turned on for the very first time, that fast success may not happen immediately. An installer completes a micro-soldering job under a microscope, cleans the board with isopropyl alcohol, reassembles the shielding, and presses the power button expecting an instant boot. Instead, the console screen stays completely black. On the mod chip board, the debug LED begins to pulse a steady, methodical yellow. 5 seconds pass, 10 seconds pass, a minute passes. The console appears stuck. This brings us to a fascinating engineering challenge in hardware security. How does a $3 microcontroller adapt to physical variations across installations? While microprocessors roll off fabrication lines under standardized architectural designs, subtle variations in transistor threshold voltages and gate propagation delays naturally exist across silicon wafers. Furthermore, installation geometry, such as the exact length of flex cables, solder joint impedance, ambient temperature, and the parasitic capacitance of surrounding motherboard decoupling capacitors, can shift how a voltage pulse propagates through the power rail. A power starvation pulse that bypasses security on console A might crash console B instantly, or have zero effect on console C. Hard-coding fixed timing values into a mod chip was insufficient. The chip had to learn its target environment. To overcome this physical variation, developers writing open-source mod chip firmware, such as Spacecraft NX, built adaptive calibration routines directly into the chip's code. The firmware tests candidate glitch timings, observes whether the expected boot state appears, and retains timings that prove reliable. Those learned parameters are stored internally in non-volatile memory, allowing later boots to complete much faster. During an initial setup phase, the mod chip tests timing offsets and pulse durations, observing bus lines for expected boot signals. If the voltage drop is ineffective, the CPU proceeds toward normal boot, prompting the chip to reset and adjust parameters. If the drop causes a system freeze, the chip resets and refines its timing range. Depending on the specific installation geometry and board conditions, this initial calibration sequence can take time to settle on a stable configuration, but once a reliable timing parameter is found and saved, subsequent cold boots load that saved profile to execute the glitch quickly. Here lies a striking irony. Millions of silicon processors were mass-produced under standardized designs, assuming uniform behavior guaranteed uniform security. Instead, an inexpensive microcontroller adapts to individual board conditions and power delivery variations, probing, listening, and adjusting until the execution path opens. When this hardware exploit spread across the internet, Nintendo faced an operational nightmare. The vulnerability was rooted in the unchangeable physics of silicon power delivery. As long as the Tegra processor required electricity to function, voltage fault injection remained effective. Unable to fix the flaw with software updates, Nintendo responded with board revisions and aggressive legal action. On the motherboard level, subsequent manufacturing layouts and component coatings also had the effect of making manual installation significantly harder. Surrounding surface mount components on certain board revisions were coated in thick, hardened black epoxy underfill, requiring modders to use specialized chemical solvents or careful heat to expose connection pads. When Nintendo launched the Switch OLED model in late 2021, the motherboard routing placed the primary DAT0 memory bus trace in the inner copper layers of the multi-layer printed circuit board. Modders could no longer solder a wire directly to an exposed surface trace on the board. Hardware modders responded by engineering ultra-thin microflex ribbon adapters. These paper-thin metal adapters were designed to slide directly underneath the surface-mounted BGA flash memory chip, making contact with a single microscopic solder ball without requiring the risky procedure of fully desoldering the NAND storage chip. On the legal front, U.S. authorities criminally prosecuted Team-Xecuter, while Nintendo pursued separate civil litigation. Key members of the group were indicted on federal wire fraud and conspiracy charges. Gary Bowser, a prominent spokesperson for Team-Xecuter, was arrested in the Dominican Republic, extradited to the United States, and sentenced to 40 months in federal prison. The court imposed $4.5 million in criminal restitution, which sat alongside a separate $10 million civil judgment from Nintendo's civil litigation, a financial burden totaling $14.5 million. Taking down Team-Xecuter's commercial enterprise did not end the mod chip ecosystem. Instead, it triggered an open-source explosion. Independent hardware developers realized that expensive proprietary FPGA boards were unnecessary. Open-source contributors working on projects like Picofly recognized that a mass-produced $3 microcontroller, the Raspberry Pi RP2040, possessed a key feature. The RP2040 featured 8 deterministic programmable input-output, or PIO, state machines. These hardware PIO blocks could be programmed to handle precise signal timing and trigger MOSFET pulses with hardware accuracy. The Picofly project demonstrated that off-the-shelf microcontrollers running open-source firmware could perform voltage fault injection across Switch hardware models. The financial barriers to entry dropped significantly.
The widespread availability of open-source glitching firmware transformed hardware hacking from an underground commercial enterprise into a global community effort. This created an ownership paradox. For Nintendo, hardware modification represented an economic threat, a gateway to software piracy that undermined their business model. But for many developers and enthusiasts, modifying the Tegra processor was about consumer rights, digital preservation, and the freedom to run user-chosen software on hardware they purchased. Beyond running custom code, modders used kernel-level access to transform the device. The Homebrew community ported alternative operating systems. By booting payloads directly from the microSD card, users could run Linux and Android distributions, turning the handheld console into a tablet PC, capable of web browsing, productivity tasks, and media streaming. Independent developers created custom tools that allowed repair shops to diagnose hardware faults, back up user data from damaged boards, and preserve titles from digital storefronts. Custom tools allowed users to adjust thermal and performance profiles, overclocking the Tegra CPU and GPU to improve frame rates in demanding games. However, this homebrew ecosystem existed alongside widespread game piracy, and one of the most significant conflicts didn't take place on the handheld console itself. It unfolded on desktop PCs. Emulation commonly relies on cryptographic material exported as prod.keys, together with title-specific keys used to decrypt individual software packages. On unpatched original Switch models, the early Fusée-Gelée exploit already allowed users to dump these cryptographic keys. Voltage fault injection on Mariko consoles expanded that key dumping capability to patched hardware revisions, allowing users on newer Switch models to extract their system keys using custom payload scripts. As these keys circulated online alongside game dumps, PC emulation experienced rapid growth. Emulators like Yuzu and Ryujinx allowed users to run Switch titles on high-end PCs, often at higher resolutions and frame rates. Nintendo's legal response was decisive. In early 2024, Nintendo filed a federal lawsuit against Tropic Haze LLC, the development entity behind the Yuzu emulator. Nintendo alleged that Yuzu's design facilitated piracy by requiring and integrating key decryption mechanisms to bypass technical protection measures. Tropic Haze agreed to a $2.4 million consent judgment, permanently surrendering the Yuzu domain, shutting down development, and deleting its code repositories. Later that year, Nintendo reached an agreement with the lead developer of the Ryujinx emulator, resulting in the project stopping development and its official repositories being taken down. Concurrently, Nintendo targeted unauthorized software distribution networks, sending DMCA takedown notices to GitHub repositories, hosting payload injectors and key dumping tools, forcing software archives to move to decentralized mirrors. With the launch of the Nintendo Switch 2 on June 5, 2025, powered by a custom NVIDIA processor, hardware security has entered a new phase. Semiconductor architects designing modern SoCs recognize that software checks alone are insufficient against physical attacks. To counter physical fault injection, modern chip designers can integrate hardware-level glitch sensors directly into the silicon wafer. These security circuits include onboard clock frequency monitors, core voltage drop sensing loops, and thermal monitors. If a fault circuit attempts to starve the core voltage rail for even tens of nanoseconds, hardware sensors detect the electrical anomaly instantly. Instead of allowing instruction evaluation to corrupt, the hardware sensor bypasses software logic entirely to trigger an instant hardware reset, stopping the attack at the physical level. Yet the lessons learned from voltage fault injection extend far beyond video game consoles. In academic research, such as studies analyzing Tegra T210B01 SoCs, researchers demonstrated that this class of physical attack affects broader embedded hardware platforms. The Tegra architecture is utilized in embedded systems, including automotive platforms such as Tesla's hardware modules and Mercedes-Benz infotainment systems. By applying targeted voltage fault injection to Tegra T210B01 chips in laboratory environments with direct physical access, researchers successfully bypassed secure boot chains, re-enabling testing bootloaders to extract keys and gain execution control.
This research demonstrated that physical fault injection is a fundamental hardware vulnerability class spanning consumer electronics, industrial controllers, and automotive platforms. The story of the Nintendo Switch voltage glitch illustrates a fundamental truth about modern digital security. For decades, software security has relied on the concept of hardware abstraction. Software engineers write code under the assumption that the underlying silicon processor provides a perfect logical execution environment, that a binary 1 will always remain a 1, that a binary 0 will always remain a 0, and that instructions execute predictably without physical interference. Multi-billion-dollar security architectures are constructed on the assumption that digital logic is completely separated from the physical world. But silicon is physical matter. It is subject to the laws of thermodynamics, electrical resistance, capacitance, and atomic physics.
It depends on microscopic copper traces, precise voltage levels, and the flow of electrons.
When a microchip is pushed to its physical limits, when it is starved of power, subjected to electromagnetic pulses, or manipulated in its clock timing, the logical abstraction breaks down. Nintendo spent massive resources over nearly a decade developing software patches, burning eFuses, encrypting bootloaders, and revising silicon chips. They constructed a multi-layered security architecture. Yet a $3 microcontroller starving a microchip for less than a millionth of a second demonstrated that software security is always bound to its physical host. Software can be made mathematically flawless, but as long as hardware exists in the physical world, physics will always have the final say. And Nintendo isn't the only tech giant that faced a physical security vulnerability. When engineers attempted to lock down the PlayStation security hypervisor, an unexpected oversight exposed the system architecture. Click right here on screen to see how that security model was analyzed and dismantled from the inside out.